If we have a strong acid in solution, super easy to find the pH of that solution. Weak acids, going to be a bit more tough, because not every single one of those molecules is going to break apart to form H plus and whatever the counter ion is. So when we're trying to work out the pH of a solution that contains a weak acid, we have to start thinking about it like a chemical equilibrium, because in fact it is a chemical equilibrium. There's an equilibrium between the reaction that dissociates the acid and the reverse reaction that puts the acid back together. So there is a very, very common generalized acid dissociation reaction that looks like this, that we are going to use dozens of times throughout the rest of this class, mainly in this chapter, but also in the next one a little bit as well. And it is just some generic acid reacts with water to form the conjugate acid and H+. And we don't actually care what A is. A is not going to have an effect on the stoichiometry here. It's not going to have an effect on, whether the water reacts with it or not. Like it's not having an effect on anything except that it changes the numerical value of K. Whatever the hydrogen is bonded to, K will vary based on that. But in terms of the actual reaction itself, we don't care what A is. And so we're just going to leave it as A, so we don't have to write out all the rest of the molecule every time. So we're going to have HA, our weak acid, reacts with water to make the conjugate base and the conjugate acid, which is H+. And then the reverse reaction is just the conjugate base and conjugate acid reacting to form water and the original acid. So the equilibrium expression for this equilibrium is H+ times A- over HA. The water gets left out because it's a pure liquid. Again, pure liquids get left out of equilibria. And so this we are going to become best friends with, because we're going to do a bunch of stuff with this throughout the rest of this chapter. This equilibrium expression is going to become very familiar to you. Because it's so commonly used, and it's used in lots of different situations, and pretty much anything that involves an acid, you're going to see this equilibrium. We actually give it a special name, so we don't call it Kc, we call it Ka. So the Ka is what we call the acid dissociation constant. It's the equilibrium constant for this equilibrium that is describing the dissociation of the acid. How much of the acid is dissociating and how much of it is staying together as HA. It's essentially the ratio between those two. It's not directly a ratio, though, because you do multiply these two together, but in a sense it is. So these Ka values, this acid dissociation constant, it can vary dramatically from one molecule to another. So chlorous acid, for example, is getting pretty darn close to being a strong acid, but it's not quite there. It has a Ka value of about 1/100th, essentially, 1.1 times 10 to the negative 2. That's definitely one of the higher acid dissociation constants you're going to see. Nitrous acid is decently up there as well, along with fluoric acid, with values around 10 to the negative 4 for their Ka. But then you'll also see things like hypochlorous acid, which is almost identical to chlorous acid. It just has one fewer oxygen, and it has a Ka value of 10 to the negative 8, which is way lower. And then other things like hydrocyanic acid, which is nasty stuff. It's like, cyanide's not bad enough. Let's make it into an acid. So that is 5 times 10 to the negative 10. So very, very low acid dissociation constant, which means that if you put hydrocyanic acid in solution, very few molecules will dissociate. Some will. There'll be a very few that do, but the vast, vast majority are going to stay as the whole molecule. The larger the Ka value, the more molecules are dissociating, and the smaller, the less are dissociating, the fewer are dissociating. So this is a very limited list here, by the way. There is a much more comprehensive list in, I'm not sure if that appendix letter is correct. That might have been from an older edition of a book that we were using, but it's in an appendix at the back of the book for sure. You can find it there. All right, so let's talk about how we use this thing. So if we're trying to find the Ka, and we are given the pH, it's actually pretty straightforward to determine the Ka. So for example, if we're told the pH of a 0.1 molar solution of formic acid is 2.38, and we're asked to calculate Ka, what we're going to do is we're going to say, well, any weak acid is going to have this generalized acid dissociation. So even though they wrote out the whole thing here, this is just H plus and A minus and HA. That's what those are. These two are the same, except this is now missing an H plus when you move it over here. So that is what we have there, just the basic acid dissociation. So to calculate Ka, we need to know all three of those concentrations. We need to know what's the concentration of H plus, what's the concentration of the conjugate base, and what is the concentration of the original acid. Now, thankfully, because we're given the pH here, we can find the concentration of H plus, because that's what the pH is based on. That is literally where we get the pH from, is the concentration of H plus at equilibrium. So we can use the pH to find that, and because of stoichiometry, we know whatever the concentration of this is, the conjugate base is going to have the exact same concentration. Because that's just, again, basic stoichiometry. We're only getting this molecule from one place, and it's from the dissociation of the molecule. And so however many dissociate, that's how many we get. So if we go ahead and do that, if we plug the pH into the pH equation here and solve for H plus, what we get is 4.2 times 10 to the negative 3. So again, what they did there is they just brought the minus over to the other side, took the anti-log of both sides, and that gave them this value, which is equal to both H plus and the conjugate base. And so we're going to then take those numbers and plug them into an ice table. So we know from the problem that we initially started with 0.1 molar of the acid, and since we weren't told anything about the H plus or the, let's see, that would be formate, I guess, because I think they said it was formic acid. Yeah, so that'd be formate. So because we weren't given any initial information on these two, we just assumed that there's none of them. We now know how each of those things are going to change because we know at equilibrium we have these amounts. And so really we probably should have put those two in first before we put the changes in, because we know what those are at equilibrium, so we know they must have changed by this amount, which means that the formic acid had to have changed by the same amount but negative. However much of that stuff was made, the same amount of the formic acid was consumed. And so if you then take this change and apply it to 0.1, what you find is that it's pretty much still 0.1. Like, it's a little bit less. We maybe could write that as 0.096, but in the case of this example, they go ahead and just keep it as 0.1. So then to find Ka, we're just going to take these three numbers and plug them right in. So the H plus and A minus concentrations go on the top, the HA concentration goes on the bottom, and we get 1.8 times 10 to the negative 4. And that is our Ka value. Now, those of you that remember chapter 13, where we were talking about just generalized equilibria, you might remember that we had two different types of equilibrium problems that we mainly focused on towards the end of the chapter. And those were questions where we were given equilibrium concentrations and then had to find the K value. And then the opposite, we were given the K value and had to find the equilibrium concentrations. This is essentially the exact same thing we're doing here. We weren't just given an equilibrium concentration, we were given a pH instead, but like I said, the pH is directly related to that equilibrium concentration. And so really we're doing the exact same thing we did in the last chapter, just applying it to acids and bases. All right. I think I'll save this one for the next video, because this video would be pretty long if I put both of them in. But in the next video, we're going to look at that other example that I just mentioned, where instead of knowing the equilibrium concentrations, we're going to find the equilibrium concentrations given an initial concentration and the dissociation constant, the equilibrium constant. So we will take a look at that in the next one.